Carl Schattke has built up his expertise in electronics and PCB design over the past 44 years. He's a CID Plus certified designer and loves to share his skills and knowledge with the world. Throughout his life, Carl has worked on thousands of circuit boards supporting all types of industries. For 10 years, he ran TLC Design, a service bureau that supported over 100 clients. He also spent time at ASIC Designs, where he worked on modems, notebook computers, personal digital assistants, and many embedded systems. Carl also designed reconfigurable memory cards at Neuron, a startup that was later acquired by Intel. There, Carl moved from the networking equipment to sort test engineering, where he designed bare wafer sort test solutions. In his current role, Carl designs computers, controllers, sensors, power electronics, and high-speed communication systems for one of the world's leading electric car manufacturers. Carl remains an active PCB design consultant and works on a variety of other projects in his spare time. Outside of work, you can find him spending time with his wife and 4 children, cycling and practicing martial arts. Ladies and gentlemen, please welcome Carl Schattke.
Thank you, and hello everyone. It's good to be here. I'm going to start out with a couple of jokes. I'm a dad, as they said in the little intro. I have 4 children, so my first joke is a design rule joke, since my talk's about making rules and breaking rules. So, why did the track pick up the pad? Because it was a cute angle. All right. And so when should a scientist stop telling jokes? When he gets a reaction. All right, so we're going to get into the talk. All right, so actually 46 years designing circuit boards. I've been doing this a long time. My dad, as we mentioned earlier, was a designer, and he had a bunch of engineers that worked for him. We called them moonlighters in those days. They were guys that wanted to earn extra beer money. And usually the designs were done with a beer on the side of the table and a cup of coffee and a cigarette, from my recollection. And my dad would have these designers working for him, and he'd keep them busy, and jobs would come in. And when the job came in, my job was to check the design. So we would make a blueprint of it, and I would grab a yellow pencil, and my dad would grab a yellow pencil, and he'd have the schematics, and I'd have the board, and we'd start yelling it out. And he'd yell out, U1, pin 2, and I'd go to U1 and pin 2, and I'd follow it, and I'd say U3, pin 4. And then he'd go U3, pin 5, and he'd take me, to the next one, and we'd go through the whole layout. And if there was anything that wasn't yellow on the artwork, that was wrong. And if there was anything on the schematic that wasn't yellow when you were done, you better find out what happened. And those were errors. And that was the original design rule checking system. It was 2 men sitting down, or women, but very few women in the industry back then. And we would go through it point to point and check it. And it's still not a bad practice, but it's antiquated now, thankfully. That was, it could, on a large design that took maybe a couple months to tape up, it might take like 1 or 2 days of actual work, calling out point to point, like all day long, just following that routine, one point to the next. So I did several hundred layouts like that, and from the mid-70s into the mid-80s, and then this thing called CAD came along, and my first CAD system was a Xerox Expert workstation, and Xerox had this $60,000 computer and $80,000 software, and I'm like, okay, I'll try this CAD thing and we'll see where it goes. You don't hear the word Xerox Expert CAD Station now for a reason. It was replaced by much better software at a much lower offering price. When you routed in Xerox Expert, it was black and white, so you can imagine the problems there. One layer would be solid traces, the other layer would be dashed lines to represent the other traces. Now, if you had a short trace, this became a problem because you didn't know if it was dashed or if it was solid. It made it very interesting to do design. So that particular design software, we landed a client that wanted a point of sale terminal done. And it was a fairly extensive board for the time, and it was integrated with, computer communications for order, it would keep track of, it was a modern system for the day. And they wanted it done in CAD. Like, they were very adamant that they wanted this done in CAD. And I probably could have done it manually in about 3 to 5 weeks. And I'm pretty sure it took us about 3 months to get that design done in CAD. So that was my early investment into CAD, and you can imagine the payments on that much software and hardware. And I quickly realized that this wasn't going to be a very economical model for my business, and I asked Xerox if they would take their system back, and fortunately they did, and they didn't hold me to the contract, so I was able to stay in business. Months later, an engineer that I'd been working with for a long time, he had bought the ProTel software, and he took that and he said, "Carl, you should check this out." I'm like, "Okay, let's look at it." And he showed me, and we had 4 trace widths, 15, 30, 50, and 100 mil traces. That was it. And you had pad sizes, and you could put down tracks and pads, and it was all CAD. That was what I call early CAD. But that was the ProTel software in the very beginning. And if you wanted something wider than 100, you put down 200 mil tracks, or wider, and you'd stack them. So many of those same initial commands are the exact same ones in the Altium tool today. So here it is, 34 years later, and we're still using the same commands from that original ProTel software. So the fact that it survived when so many others have gone other places is amazing, and the fact that it's continued to grow and get better. So it's basically had a couple major iterations. It went from ProTel to Altium Designer, and then, actually it's ProTel to ProTel for Windows, which was like a 3.1 Windows version. It was the very first Windows software for printed circuit board design. And then after ProTel for Windows, then we had Altium Designer, which is kind of the version we have today. And then, it's migrated into Nexus. And over the years, that tool's just gotten amazingly fantastic and better in so many different ways. But the thing about ProTel, which turned into Altium in 2001, is that this is a company that's always listened to the user base. And they've always listened to the suggestions that we had. So, like one of the suggestions I had a long time ago was like, you should really automate this process of going from board, from schematic to board. And I told them, like, we should have a table here, and we should have a table here, and we should say this goes to here, and like just keep track of everything. And they did it, and that's what you see today in Altium Designer. It's like, these are huge changes in fundamentally how the software is architected, but they did it, they made the changes, and the company's grown. So I had a service bureau for 10 years, and I sold that, and thought I was going to get rich in something else, and it nosedived, and I didn't. I went to work for somebody else, and then built that up, and it always comes back to me, like my best use as an employee is as a printed circuit board designer, because I love it, and I'm good at it, and it's fun, and I am excited to make products, and I've made now thousands of different designs over the years in almost every conceivable field, from baby monitors to grave markers. I made a grave marker that would talk to you when you went to the grave, so think about that on Halloween coming up here. And baby monitors. I did the world's best-selling baby monitor at one point. It's really fun to work with engineers that are passionate about what they want to bring together, and it's also really fun as a designer to be able to make that happen and make it possible. So I was in the Chicago area originally, and then worked for this startup, get a call 11 o'clock at night, this guy calls me up. I'm on a board, and I'm like, this guy says he needs some help. And I said, okay. He's in Notre Dame, and I'm in the western suburbs of Chicago. So I drive to South Bend, Indiana, and it's like snowing a little bit. But I get there around midnight. We talk, and about 2 o'clock I drive home with a bag of, with a schematic and some information. And I get home, and then the next day I work on it. Next day I work on it, and it's done. It's a little 4-layer board and display and processor and so forth. And I put this together, and I send it to him. I said, well, what do you think what you got? And I found out later he was really thrilled because they had spent 6 weeks with another company that did it in 6 layers and said it couldn't be done in 4 layers. And I gave it to him, and later on I heard he said to his partner, he goes, I think we found our PCB guy. And turns out that company, we did a number of configurations, but we did a reconfigurable memory board that sped up SSL encryption. And before the internet was the internet we know today, it took a long time to do a transaction. You imagine going online to buy something. If it takes a minute, you're like, yeah, I'm out of here. But if it takes 3 seconds, then you're like, sale done. They got your money, and it's all over. They're just going to ship it to you. So there was a real tangible benefit to that product. And Intel bought that company for a lot of money just 18 months later. So it was pretty thrilling, and that's what moved me from Chicago to Silicon Valley. And I ended up staying in that network equipment division. And 18 months later, they closed it down. And I don't know anybody. I've been nose to the grindstone designing boards. And I'm like, hey, software guy, who uses your software here? Oh, okay. So I call him up. I go, you guys interested in another board designer on your team? I go, yeah, we are. We're actually looking for somebody. So I go and interview. And I had a job before I walked out the door. And they closed our network equipment division down. But I was the first person. I had a job in 6 days after a lot of prayers. All right, so that's how I wound up at Intel, and then I stayed there, and they closed that. So I worked in that sort test group for a number of years. We developed an auto router that was able to auto route multi-chip modules, and then we also did an entire process review and change, and we went from a 30% error rate to 0 errors for 2 consecutive quarters. So I was real proud of that accomplishment. And we later sold that methodology to another company for $1 million it was valued at. So our talk today is about making rules and breaking rules, but I'm not going to teach you how to write rules in this class. It's an hour, it's Keynote. We're not going to go into depth in how you write a rule and how that works. If you go online, there's some fantastic tutorials on the Altium website, and there's a couple classes that do dive into that here at AltiumLive. But what I do want to talk about is how do we get our rules? How do we think about rules? How do we use rules? How does the software change with the rules that we use? And then where are we going to go in the future with rules? Like what kind of rules are we going to need? And where do we want to go with that? So that's what this talk's going to be about, and we'll get into it. So the Dalai Lama said, know the rules so you can break them effectively. All right, so the ancient PCB design rules were, this gridded mylar and precision slit tape and photographic stickers and individual donut pads, and we'd do the work at like 2 to 1 or 4 to 1, and then we'd bring it to a photo tooler that would reduce it and color separate it. And our design rule was like a ruler. We'd use a ruler and we'd measure it, and our library was a bunch of templates, and we would get that artwork back, and then they would put it into a machine that would bomb site each drilling location, and we'd organize that, and then you'd literally like draw a path. If this is your 15 mil hole, you'd like draw that on there in one color, and then you'd do like 30 mils, and that'd be another trace, and you'd go through each one, develop your tool, and that's how it was done in those days. And you had a person whose job it was to do that. And my dad had a printed circuit board manufacturing plant, so I did everything except for the gold, because the gold was it had cyanide, and cyanide gas can kill you, so only the chief chemist was allowed in the gold room for the gold lab. But every other process I've done, I've dipped boards and image boards and inspected boards and touched up boards and designed, boards for that process. So you really learn a lot about the process when you go through and actually do the work and get a chance to see where errors happen in the production of boards. And you see the wider the spaces are between your traces, the more reliable that board's going to be. The wider your traces are, the more reliable that board's going to be. So those kinds of things have stuck with me as a designer over the years, is like how to achieve high reliability and low cost, because it's no accident to design right. So what were the drawbacks of this old design methodology? Well, it took a lot of skill to do the drafting of the layouts. The placement would typically, you'd make paper dowels for each component, and then you'd move those around in the space that you had. And when you had something you liked, you'd either tack it down with a piece of tape or be very careful not to sneeze. One sneeze could ruin your whole day. And you'd just be real careful, and then you'd move things around, and you might tape the different dowels together once you got them. And then once you figured out your master placement, let me go. So here's a drawing here in the foreground of one of the placements that I did. So this is gridded mylar, and then this gridded mylar here. You could see, like, we would bias the layers. So the green, traces are going, red's this direction, and then the green is this direction. And we'd use a different direction for each layer. And then, like this particular one is like a card. So you see, like, on this end is, an edge connector, and that would be gold plated and fit into a rack. And this board behind it is a tape up, and this is another tape up here. I brought these to AltiumLive down in San Diego because, I told Judy I have these things in the garage. I haven't dug them out in years. She said, "Oh, you should bring that." And fact is, how many people here have ever seen a taped artwork? So we got about, I'd say 3% of the audience, maybe 5% if I'm generous. How many people didn't know this was even done this way before today? Be honest. You can raise your hand. Okay, so about the same number. So a lot of people did know that this was how it was done. But, this is how we design the computers that we use to design more computers now. And that's how it was. It was like you start from Earth and stuff gets built up, and we all ride piggyback on somebody else's shoulders at one time. And for me, one of the most inspirational stories I have when I started being interested in engineering was the moonshot. So in 1969, I'm 8 years old, and the astronauts come back from the moon. And I'm in Chicago, and there's a ticker tape parade, and I'm on my dad's shoulders, and there's thousands of pieces of ticker tape coming down. That's the same thing that we use for the Exelon drill tape. It's just for stock market use. And they drop these rolls of paper from the high stories of the building, and they like spin down in spirals. And when we left, it was like as high as my dad's knees, just ticker tape everywhere. And I'd never seen such admiration for science before in my life, and probably never will again. But it was so fantastic to see, men that went to the moon and came back. And that was a super interesting time, and it had a lot to do with my excitement for engineering and what could be done. Another story is when I was young, my dad and his friend, his friend developed like timing systems for auto racing, but he started on a new project. The new project was a smoke detector for home use, and there were some commercial smoke detectors, But this was for home use. And I'm like, well, why do they want to do that? Well, it wakes people up if there's a fire in the house, and it's going to save a lot of lives. And now you can't buy a house or sell a house without a smoke detector in it. And nobody would think of sleeping in a place that didn't have a smoke detector. But, you know, that has definitely saved millions of lives over the years. And as engineers, that's the kind of thing that we do, is we create something, add our bit of technology to it, and it really, really helps a lot of people when we get done. So that's one of the reasons I really like engineering. So I was showing these things to a group of young students at PCB West in AltiumLive in San Diego. And, you know, it was, you know, you can see in the slide on the right, you know, like these, you know, like this was our original library system. As you had, you know, like this was a 2-watt resistor, and this was a 5-watt, and that was a 3-watt and a 1/4 watt. And like most of your resistors were 1/4 watts in those days. And then you would draw that on the layout like you saw on the previous page. And then you would color separate it and turn it into film like this. And then you'd do a drawing, and you know, you'd like manually draft your instructions for the board fabrication. Now we have draftsmen in Altium, you know, and we, you know, we've automated that. So this was my original Altium software here, you know, Protel Auto Tracks. I think I was user 600 or something like that. And so early CAD was very crude by today's standards, very crude. Like I said, it had like 4 trace widths, and that was it. The systems that were prevalent at that time were Telesys and Protel, and AutoCAD was used a lot, and people would take that pencil layout, and sometimes they would use a Gerber digitizer for that, called a PC800, and then they would digitize that, and that would create the photo tooling. They didn't have the laser plotters then. They used a Gerber pen plotter, and Gerber is light on, light off, draw, or flash. That's it. And there's a wheel of 24, and you had a wheel of 24, and if you exceeded the wheel, you had to get another wheel, and that was more money. So you tried to design in less than 1 wheel's worth of fixtures. And then now, you know, we think of Gerber 274X. This was the next stage of development, and we moved from this early crude CAD, but it did enable point-to-point, you know, design rule checking. So instead of having to get a yellow pencil out, the computer did the work, and we had simple spacing rules. It would check for shorts, and it would check for opens, and you know, this was what you checked back then, and it would generate your pick and place files. It would generate you know, a drawing from your mechanical layer, and you'd, you know, be able to do that. But the key thing that it enabled was repeatability, and it reduced the skill level that was required to do the work. So now more people could join the industry and partake of this. You didn't have to be an expert at carving tape. You would be able to use the CAD tool to do that. So it was very repeatable. The pioneers are the ones who get the arrows in their backs. Yep, that's what Brian Roberts said. He's right. So yeah, there was the growing pains with that. But then the computers got better, and the software got better. And in the late 80s, early 90s, there was a revolution of really quality tools coming on board that were able to do very complicated, extensive, challenging boards. And we saw a whole new generation of designs take off that were way more complex than what was done in the 70s and mid 80s. And this was when notebook computers were being designed and improved, and modems, and a lot of projects that had like wide parallel buses back then. High-speed data transfer wasn't really a thing yet, so everything was very wide buses, and you had a lot of designs that were just very large, devices. And then FPGAs came on board in the 90s, and people started using those. And so we used to have tons of gate logic that would be on the boards, and you needed a lot of boards to have a complex system. So now with FPGAs, you needed a lot less designs to be able to do the same functionality. So there were less designs, but they were way more complicated. And now, and then the computers became much more advanced, and we started using auto routers to be able to do a lot of the routing for us. And so the Spectra router was pretty much state of the art in those days. There were others. There was like a Mastech router. But the Spectra router, and then you could drive that with like MakeDo, it would let you write very specific rules for how to do the timing and set up point-to-point rules and things like that. So then intelligent polygons came on. So early on in the Protel system, you could draw a polygon, but it would be a series of hatched traces on top of each other. Now we still have that as an option that nobody uses, but that was what we had available to us back then. And then then companies started to get wise to the need for libraries, and we had the IPC come along, and there was IPC standards for libraries, and then the libraries, there were third parties that would provide libraries, and these could augment what you had as a personal library. Most people didn't trust anybody else's libraries. It's still like that today. How many of you trust your libraries? So I see about 20, 30%. The rest of you check carefully, and then you trust them. Libraries are still an issue. Getting parts built, like when I see design rule errors, I would say a good majority of are from new parts that weren't designed correctly, like where there's silk screen too close to a pad, or there's an incorrect courtyard, or something's wrong. Like, I don't trust data sheets. Rick Hartley earlier said he doesn't trust data sheets until they're proven to be correct. Same thing with your library parts. As designers, we know that's our building block. We want to make sure that those parts are right before they go on our board, because one bad part, one bad board, and that's not a good equation, especially when we're paying a lot of money, to get prototypes built. It can be thousands or tens of thousands of dollars. The constraint-based rules are more the norm now than they were with these second-generation tools. The constraints could be hierarchical in nature, where it might be board, layer, class. So you go increasing differentiation to increasing control over the functionality. So that's one methodology that's employed by like the Spectra router. Our methodology with the Altium tools is like a Boolean logic to define what the entity is, and then that will be applied to a class of entities, and then that's going to be put into a priority, and then it's going to be segmented based on the type of rule functionality you're looking for. So this is extremely useful for high voltage designs, extremely useful for parts that have multiple different types of circuits on them. It's very useful for highly complex rules. It's also super confusing because you could see something, if you don't put things in the right order, you have a problem. So it's very important to look at how you're setting up your rules in order to get the right results out of your design. So the next wave, I call the nth wave of CAD tools, and that's like where we are now and where the future's going. And we're going to come back to that later. So there's these, I explained the two different rule systems, like the Cadence way of doing things, the Altium way of doing things, and it can be hard to manage these. The blankets, are very powerful. You can put rules on a lot of things very quickly. You can drop, nets into the blankets. You can have endpoints of traces into the blankets. We handle very, very complex rules, but sometimes this complexity will get away from us. We can also integrate with, analyzing tools and things like that. So Altium has two different kinds of rules that we think about. So unary rules are one entity, and they're typically applied in the schematic. And then we have binary rules, and binary rules are typically applied in the printed circuit board. So the unary rules would be things like for routing, trace width, length, electrical rules that you can apply directives in the schematic that will then place into the board, like classes and groups and differential pairs are best defined in the schematic. High-speed rules would be best put into the schematics. And then PCB rules are what we consider binary. So binary rule is defined by one entity interacting with another entity. So schematic rules are one entity and how it's treated. Binary rules are how two different things are going to interact. So the PCB binary rules would be like pad classes. So if I have like non-plated through holes and I want to create a pad class for that, I'd highlight them first, and then I'd go into the tool and I'd move those I'd create a class of pads that's NPTH, and then I'd hit the double arrow, and over the selected things would go. Now I have my pad class. Now I can write a rule, and I say keep all copper 0.3 millimeters away from any NPTH pad. So now I've got my copper clearance to that hole that's being drilled. So region-based rules are, I can make a region around like a BGA, and I can set a different rule for that based on routing within that. And manufacturing rules are things like acute angles. We can control that. Usually, I'll set that acute angles to like around 45 degrees or so. And I just want to find sloppy routing that's coming in at like an odd angle. The board outline clearance, again, don't put the copper right up next to the edge of the board. It's going to tear up the router bits. They don't like to route copper. And then allow them, so UL is like 0.25 millimeters away from the edge of the board, or 10 mils. But what we want to do is typically like double that, be generous with the edge of your board. There's a tolerance to that routing, and you'll help yourself if you keep things away from the edge. And then hole size. Now, if it's a really large hole, typically that's going to be part of the router profile. Large holes, large slots. Typically, that hole size, up to 1/4 inch is fine to drill, but generally, if it goes over that, they're going to want to be routing that rather than drilling it. Hole-to-hole clearance is an area that your board manufacturer is going to really be looking at that as far as how manufacturable that board is. What's the minimum hole size, and then what's the distance between those holes? And it's also going to have a lot to do with your reliability. So you want to check with your board manufacturer. How many here design high volume boards? And how many are here designing like test boards where you're ordering like less than 10? Like that's your average thing. So less than 10. How many are ordering maybe like 500 to 1,000 a year or something after it gets done? Okay, so a pretty good mix. Like I thought it might be more high volume, but it's a pretty good mix. How many here have never designed a circuit board? So everybody here has. That's awesome. So So, the other thing that we want to look at with the manufacturing rules is like minimum annular ring. So there's a tolerance on the drilling, there's a tolerance on the plating, there's tolerance on the imaging. You add all that up, they're looking for at least 5 mils in volume. They prefer 6, but these are the kind of ways you save money. Like asking a board vendor what they can do and what they should do is a lot different. You want to really focus on, for high volume, what they can do reliably. And also, so there's something called CAF, conductive anoidic filaments. These are created when there's high voltage, and high voltage is pretty much anything over like 12 volts can cause this effect. And it draws ions from one node to another. And if there's any imperfection in the printed circuit board substrate, like glass that hasn't been filled in with epoxy, those ions will travel through that. If you drill, you fracture that. So when you drill fiberglass, it breaks, right? And that creates air pockets. Those fill up with ions, and those will drive with force. Metal ions will try to cross that barrier, and that's going to ruin your reliability. The other thing that happens is some metallurgy will create spikes on itself, and you'll see errors that'll happen with dendrite growth. So these are a couple of the chemistry problems that plague circuit boards for reliability. And the way that we solve for that is in the design rules, by setting rules up that are going to separate these different entities far enough so we have a reliable board. And check with your volume manufacturers about what specific rules they have, but they'll give you charts, and you translate those charts into these rules. So Soldermask sliver. So Soldermask slivers are an area of the rules that if a small piece of solder mask flakes off, it can land on a pad. You solder the board. Now it's got a piece of solder mask between your lead and the pad. You have a failure mode. We don't like that. We want to build stuff that lasts. So we want to make the solder mask wide enough to stay in place. Some manufacturers will say 3 mil. Some will say 4 mil, which would be like 0.1 millimeter or 0.076 millimeter. For the metric audience we have here. How many people here are designing exclusively in metric? How many are exclusively in mils? Okay, and how many are like switch hitters? Okay, so I would say even in this audience, it's almost everybody's using metric, which is good because it's pretty simple. But the reason a lot of people like mils is they don't have to type a period. Usually mils will just be a number, whereas metric, it's going to be 0 point something. So that's the number one grievance that people have with metric for doing printed circuit board design. All right, so how do we set up a net class in rules? Well, we put a blanket around it like we see in the lower left here, and then we name it, and we put some rules in the classes below. So classes define entities, rules apply to entities that have been defined. So this is the parameter window in Altium on the right here, and that's how you do that. And then net classes, for differential pairs would be the same way, and these can be set up as either group matched lengths here or within differential pairs. So this particular one is going to set up a 1 millimeter rule tolerance between the differential pairs. So these, if there's a differential pair, one could be 1 millimeter away from the other one. But you'd set, and then this diff class 120 ohm, so that might be for like a CAN bus or something like that. All right. So also, everybody knows you need underscore P and underscore N and as a suffix. If you're setting up from the schematic, you can manually set up in the PCB, but please don't hurt yourself that way. And if your engineers are doing that, train them to not do it that way, because it's too easy to miss setting up differential pairs if you don't assign them as differential pairs. Okay, so how do we know when to apply rules and impact our, this is going to impact our design flow. So what rules do we want to use and what rules do we want to drop? So about half the rules we want to use, and about half the rules we don't care about. Sorry, Altium, I know you put the rules there, but we don't need them usually. So I would say 98% of the designs, I'm going to be using all the electrical rules, maybe some of the high-speed rules, usually all of the manufacturing rules, except for the layer pairs, unless I have a specific high-speed bus that I want to, keep on a particular pair. And then pretty much all the routing rules. If I've got diff pairs, I'd certainly be using those. And routing via styles, on any HDI board, of course you're going to be using that. But if you're not doing an HDI board, then you wouldn't need to use that. But we're going to definitely pick up our rules from there. And then we want to, the signal integrity rules, how many people are using those on a regular basis? Yeah, so 2 members in our audience are using those regularly. So it's pretty rare to use those. I would say the one exception is the impedance. Obviously, if you have some controlled impedance, you're definitely going to be using that one. But pretty much that's a rule that's not used very much. SMD entry. How many people use the fan-out tools for their BGA breakout? How many do it manually? Almost everybody's doing it manually. That's how I do it. I was just curious because the tool's there, but you can't control the results as accurately as you can when you do it yourself. So I'm not surprised by that. I would say 90% of the hands went up to doing it manually. And then how many people design their boards with test points on them for ICT? So those are the same hands that went up for high volume, right? So if you're doing high volume, you're absolutely going to be testing your boards for high volume production. And this is going to, be a lifesaver for your throughput because you get to test the full functionality of each circuit, make sure that all the right components are installed. But as designers, it's way more of a pain in the rear because we have to put a test point on every node and we have to find room for it. Ideally, we put them all on one side and we don't have to build a clamshell fixture. If it's a very dense board, we do put them on both sides. And then we save money by increasing the pitch, and we save money by increasing that pad size for the ICT. So we don't typically use the fabrication test point, or we will use the assembly test point style and the usage. And who's used the usage and seen errors coming back that it's missing a style? Who's seen that? Yeah. You know how you solve that? You put the same name in your usage in your style. That's one place where 2 rules impact each other and they're not the same. It took me the longest time to figure it out. I'm not too proud to say it took me a long time to figure that out, but that's how you solve that. Put the same name in your usage in your style, and then that problem will go away. All right. So that covers when we use rules and when we don't use them. So I think I already talked to all of this. Yeah, we already talked to that. So here's an example of a chart with a class of nets on the left and a class of nets above it, and a inner and outer layer rule for different gaps between these entities. And this is just one way to keep track of class-to-class clearances. In a high-voltage design, this is extremely important because we will get arcing across these circuits if we don't have the right gaps. So it's pretty important to get that right. So we would set these different rules up based on the requirements of this design, looking at the voltages and so forth. And then if you have a design that's got 40 classes and that's going to be 40 different entities interfacing with 40 others, that's 1,600 rules, and you have an inner and an outer. Now you have a design that has 3,200 clearance rules on it. Kind of hard to write those by hand. So, where I work, we wrote some software to kind of speed that up, and so we use scripts to create a rule generator, and then we import those rules into the design. It works quite well. So we also have complicated with rules. Like how do you go through your design and set the right rules for the widths? Well, how much current is it going to carry? How long is it going to carry it? What's going to be, how long before the software is going to clamp that down? Those are things that can reduce how wide that trace has to be. So, it's 15 amps, it has to be 30 millimeters wide. Not necessarily. If you've got software that's checking it and it can clamp it and turn it off in, X number of time domain, then it only has to be able to survive, maybe a third of that. So now instead of having to be 30 millimeters wide, maybe it only has to be 10. And, so like how we set our rules, is going to be dependent on how you've engineered, your ability to turn that, that particular power off if there is like a short condition or something like that. So we can adjust these things, and we look at like how much is it temperature going to rise. The fuse currents are typically very, very high, and but we don't want a board that's going to continuously get very hot and cold, because that's going to break that material down and it won't be a reliable board. So we have to be careful about how we do that, and we also have to be careful about the kind of materials that we spec. All these things are going to, be part of our rule set. Isolation components. So when we talk about parts that need to be isolated, we're going to look at like safety gaps for like medical products or high voltage. Keeping high voltage away from us is important. Keeping us away from the high voltage, and we typically do that by with isolation components. And we want to treat those components are typically active, but we have to write a specific rule. So in Altium, you could you can select different entities and then create an expression from that in the filter, and then use that filter and import that into the rule, and that'll write the rule for you, and then you can apply that rule to whatever values it is that you're looking for. So that's just a technique for writing rules. Why the heck am I getting all these DRCs? So who's finished a design and had more than 5,000 or 10,000 errors, right? Like lots of hands just went up. Seems like a lot of errors, right? You're like, 10,000 errors, how long is it going to take to go through those? Usually a few days. But it depends on what the rules are. And a lot of times, one rule change will fix a lot of those errors, or you'll work in, basically, almost all of us work with get it done and then fix it. That's pretty much the best methodology. Like, don't get hung up on the shorts and, like get it routed, get it done, and then be like, well, that stuff's too close. How can I change that? It's an iterative process in our design flow, and we want to use the rules to support that. So when you run your DRC, you're going to initially get a lot of errors, but then you can change either your rules, or you can change how your routing is in order to solve for that. So it's also important to know, like on a design, like what are some of the things that the tool doesn't check. So here's a large split plane that goes all the way around here. So this area here outside is 1 voltage, and this is another voltage here. So, like, I don't know how long that is, but it's a lot of millimeters, right? And so what I've done is, like, in the real dense sections, I've, got a thin trace. But where I have a little more room, I've made this a wider trace, because the crosstalk is going to be a function of the length and the distance it is apart. So increasing the distance that those planes are apart from each other is going to reduce the crosstalk. So I've definitely had engineers get their boards back that follow this like minimum trace width everywhere, and then their different voltages are seeming to couple the noise into each other, and they find out it was this. And it's not even a rule that you could check. So as designers, we need to know, like what it is we can check and what we can't check. We saw the demonstration earlier by Rick where he was showing us the best via locations for diff pairs. Well, it'd be kind of cool if you could have the tool drop in the ground vias next to those diff pairs. So like this would be a great rule to have. It's like distance, measure the distance to the return path. The new version 20 supports the checking of our traces to a ground plane. So, some of these things are already here in version 20. We're going to see them. Obviously we want to search for clean DRC and get that clean DRC. The board's done. I don't like shipping a board with a bunch of DRCs. It's too risky. How many have managers that would rather just ship before they clean the DRCs up? Everybody. Oh, so raise your hand if you've had a manager say, just ship it, it's routed, right? Like how many of you want to say go to hell? Yeah, I'm that guy too. Yeah, exactly, because it's like, it's done being routed, but it's not done. It's like, yes, you can have that, but I won't guarantee it will work. And I will guarantee that if it doesn't work, you're going to be very unhappy you spent the money on that board. Give me a day or two to clean it up. We'll put out we'll put out our, good board. Like, give me the time to do it right. Like, management usually wants it yesterday, and sometimes they have to suffer. So this is an example of, so the assembly vendor's looking for like 102.102 millimeter clearance solder mask to solder mask. But this design is like 0.074. So there's not enough room between these pads to have the right solder mask sliver. So there's a real common DRC error. And the way we fix it is we shrink the expansion on that pad to where we get the right clearance between the pads. And if this solder mask is at 2 mil, if it's at if it's at a fraction of what we would normally have as an expansion, if the registration's not perfect, the solder mask could overlap the pad. Usually solder mask registration in today's world is pretty accurate. So I feel there's lower risk at solving this way. The other way is to put a solder mask bar. How many solve this problem with solder mask bars? Nobody? No, there's a few hands that left up. So we used to do it that way all the time. Now nobody wants it that way. So I would imagine the assembly vendors have been getting back to all of us and saying, do it this way. All right. We want 0 DRCs. So what's the next generation of CAD tools going to have for us? Like, where do we see all this going? Obviously, like integrating 3D rapid, manufacturing tools is something that we'd like to see supported. Rapid prototyping is definitely a trend. Rule-based routing, that's going to get better. Intelligent automation, so that means something different to probably everybody in this room. Intelligent import and export, enhanced peer-to-peer. So being able to bring your data to your manufacturers of the board and the assembly is definitely improving. I think we're going to say goodbye to ODB++. It's kind of a very cumbersome database. It has like hundreds of files in it, and I think it's going to go by the wayside. It's proprietary with Mentor. I think the IPC 2581 is going to certainly replace it. It's one file. It's so much simpler. I don't see ODB++ being used as the mainstream thing in 5 to 10 years. You know, people are just now getting comfortable with the new IPC standard, but I think it's fully capable. I think we're going to see rules-driven libraries where you put the data of the component in and the parameters of tolerances, and I think you'll have a custom-generated footprint based on what you're trying to achieve. Are you looking for high density? Are you looking for high reliability? And I think that the library will kick out a footprint that's going to give you what you're looking for. So I think that's definitely a trend that's going to take place. I think there's definitely a trend towards more seamless integration with all the auxiliary, all these additional tools that are available for us as resources. So right now, there's probably not a person in this room that doesn't use some of these tools, for checking signal integrity, for power integrity, design for manufacture, design for assembly, the EMC and AMI compliance. There's software for that. There's RF software. There's ICT checking software. There's software to check, like what's your cost of the ICT fixture going to be. 3D CAD, integrating with, our MCAD systems. Layer stack-up software, there's HDI checking software, there's antenna modeling software, there's stress analysis software that's available to us. And chances are there's somebody, that's going to come up with some new class of checking or tools that we don't even know about that'll be on this list in 5 or 10 years. Like, this is an incomplete list. But where do we see it going? So I call it the law of progression. And the law of progression means that, like, we looked at that first wave of CAD tool, right? It was very crude. It only had 4 trace widths. Then it progressed to the windows, and then it progressed to, the computers got stronger. And this law of progression means that where things are today, they don't stay. They improve and they get better. And, like, this is how you predict where something's going to be, is there's going to be this law of progression. But sometimes there's like a eureka moment where somebody comes up with a completely new way that's novel of how to do something. We'll probably see less of that in the CAD space, but we're definitely going to see continuous improvement. Like, there's things that one CAD system does that another doesn't do, and eventually, competition being what it is, they're all going to want to get to that same point. But we're fortunate to use software that's really easy generally to use. It's super complex. There's like tons of different nuances to it, but the tools that we have are awesome. I want to thank Altium for making and designing and continuing to upgrade these tools. They've done an awesome job, and I love using the Altium software. So, other things that we're going to see in the future is I think we're going to see like diamond IC substrates. This is being used on some power devices now, and it's super hard to work with diamonds because they're so hard, but as a conductor thermally and an insulator electrically, they're perfect. We're also going to see like material science integration where 3D products will be printed and you'll have circuits inside of things. And then there will be fabrics that are smart. You'll see clothing that will support either safety, security, cosmetic. There will be wearable fabrics. Like, you'll be able to change your shirt color with the touch of a button, in the future. You laugh about that now, but it will be there in the future. And there's a whole wave of, things going on. But this is just like one area of science. There's a lot of things that each and every one of us work on that adds value to the marketplace and increases like the capabilities of what's been done before and what will be done. And it's just a really exciting time to be a part of this. And then optical computing is going to speed up the computing. Like, I still have to wait too long when I have a large design to do that design rule check. So here's a quote that I really like. It says, "Once a new technology rolls over you, if you're not part of the steamroller, you're part of the road." All right, so this law of progression is, like things are going to change and grow, and we're going to do more, and there's going to be new fields that all of us will play in. Like some of us will move from what we're doing into these new fields. There'll be new smart materials. There's a lot of very good, interesting things coming. So I want to challenge everybody here to, position yourself to contribute. Like each of you came here to AltiumLive to learn. I want to commend you for that. It's awesome to share what you do with other people and to learn from others and to teach others. So when you see something that the tool doesn't do and you wish it would, contact Altium and tell them. They will change it, and the next generation could have that feature in it. Work on those hard problems that serve humanity in unique ways. So there's products for healthcare, there's products for security, there's products for all different industries that we build and design, and they help others. And then improve your network while you're here so you can be a problem solver and also have other people that can solve problems for you. So I was reading a study, and it said the most important thing about the successful track that somebody is going to take, it's not their education, it's not how hard they work, it's their network. How many people are they connected with? How many different tribes do they run with? How can they transfer information from one area to another? That was the number one indicator of professional success. So I want each of you to really think about improving your network so you can be a better problem solver and also help others solve their problems. And then, teach and train the next generation. So today I'm up here. In the future, maybe it'll be one of you. And I think, each of us has a role where we learn, and then we bring this back to our companies and we share what we've learned with those people. So get good at that. And, that really helps us as an industry grow and develop and continue. So this last one is, a true legacy doesn't just solve today's problems. It positions others to solve tomorrow's problems. So I know that every single person in this room is a problem solver, and I commend you for it, and I thank you for attending my talk today. Thank you very much.